We are next going to talk about how we can do a hypothesis test for pi. Now, given the choice between doing a hypothesis test or a confidence interval for pi, I generally will always choose a confidence interval for pi because it gives us a range of possible parameter values for pi, and you could actually use that confidence interval to do a hypothesis test. For example, if I'm testing, for example, is pi equal to maybe 0.4 or pi does not equal 0.4, I can look to see is 0.4 in that confidence interval. If 0.4 is in the confidence interval, I would say don't reject HO. If 0.4 is outside that confidence interval, I would say reject HO. Hopefully, in an introductory stat course, you've seen how to use confidence intervals to do hypothesis tests. But there occasionally can be times where you just want to do the hypothesis test. Maybe you just want to get a p-value so you can get a measure of evidence against the null hypothesis. So we're going to talk about two brief ways to do this hypothesis test, where the first one you should have seen before in an introductory statistics course. So for example, if I want to test the hypotheses of pi is equal to pi 0, where pi 0 could be some particular value, such as 0.4, versus pi does not equal pi 0, then I can use this particular test statistic to help perform that test. This test statistic we've seen before, and this is again what you should have seen in an introductory stat course. This test statistic is called a score test. More information about how score tests come about are in my Appendix B if you are interested. And we would say reject HO if the absolute value of this score statistic is greater than the 1 minus alpha divided by 2 quantile from a standard normal distribution. Now, another way to do the hypothesis test, which depending upon your background you may not have seen before, is through what's called a likelihood ratio test. The likelihood ratio test is a very general way to do hypothesis testing. We will use that a lot in our particular course, and you will see it a lot outside of this course as well. And so the likelihood ratio test is based upon a likelihood ratio, where we look at a ratio of two likelihood functions where the numerator is the maximum possible value the likelihood function can take on if HO is true. Meaning, for example, if I was testing, is pi equal to 0.4 or not? I'm going to find the maximum possible value of that likelihood function that assumes pi is equal to 0.4. The denominator here is the maximum possible value that the likelihood function can take on if HO or HA is true. And so we look at the ratio of those two likelihood functions. And remember what a likelihood function basically gives us. It gives us a measure about how plausible particular values of pi are, or particular values of parameters in a general sense. And the larger the likelihood function is, the more plausible a particular value of pi is. So in this particular case, if let's say pi is very, very close to 0.4, if I'm testing 0.4 versus not 0.4, then I would expect the maximum possible value that the likelihood function can take on in that case to be very similar to what I get if I allow us to have the alternative hypothesis to be true. In other words, the numerator should be very close to the denominator because both times we have plausible values of pi. And so if the numerator is close to the denominator, that means I'm going to have a ratio that's about 1, so lambda is going to be about 1. Now, if instead, if I was testing again a null hypothesis of pi is equal to 0.4 versus an alternative not equal 0.4, if instead, pi equal 0.4 just isn't true, then what that's going to say in that numerator for that likelihood function, that's not going to be a very plausible value. And that likelihood function will be small relative to allowing me to have the more flexibility of what HA gives us. And so in that case, I'm going to have a ratio that's close to 0. And so in the end, we're going to actually do a little mathematical transformation of this ratio. We're going to take -2 times the natural log of lambda. A long time ago, a guy by the name of Wilkes showed that as the sample size grows, this statistic is going to become increasingly like a chi-square random variable with u degrees of freedom. In the most general sense, u is the difference in dimension between the alternative and null hypothesis parameter spaces. For us, for all the problems that we will look at in this particular course, u will simply be the number of parameters that we're testing in the null hypothesis. So in this particular case, I'm just testing one, so I have 1 degree of freedom. Okay. Then you should think about, well, what's going to happen to negative 2 log lambda then in these two different scenarios? Well, if lambda is close to 1, let's say maybe this is a ratio, so it's not going to go over, well, let me back up. It's not going to go over 1. It's always going to be between 0 and 1. And so as lambda gets closer to 1, let's say 0.95, 0.96, 0.98, take a look at yourself. What would happen? Actually program it into R. What you're going to see then, and I guess we could go ahead and do that. Why not? So I have log of 0.95, log of 0.98, 0.99, and we can see we're getting closer. We're getting more and more essentially negative. And so look what happens then if I were to take negative 2 times log of 0.95. Suppose it's 98. Suppose it's 99. And we can see negative 2 log lambda is going to get closer to 0. So that's under the scenario where it looks like the null hypothesis is true. Now in an alternative scenario, look what happens. Remove the 2 there. Look what happens as this ratio gets smaller and I put it into this transformation. So first of all, if I just do the log transformation, we can see we get more and more negative. And so when let me do this, look at negative 2 times that, we can see now we're increasing. So when I have evidence against the null hypothesis, my negative 2 log lambda statistic goes up. So what that says is then I should reject HO if I have a large negative 2 log lambda value. How large is large? Well, let's use the 1 minus alpha quantile from a chi-square distribution as our critical value. So let's take a look at a quick example here. This is with respect to field goal kicking once again. Suppose I want to test, is pi equal to 0.5 or not? I observe 4 successes out of 10 trials. I need to calculate my lambda statistic. So first of all, the numerator assumes the null hypothesis is true, the maximum possible value of that likelihood function, if the null hypothesis is true. In this case, since I only have one parameter in my likelihood function, that means the maximum possible value occurs when I have pi equal 0.5. And so I can go ahead and calculate then my likelihood function in that scenario. Now in the denominator, allow HO or HA to be true. And so what's the maximum possible value of the likelihood function essentially when pi doesn't have any restrictions on it? It's between 0 and 1. Well, that's where we calculated before. We calculated this before when we found the maximum likelihood estimate for pi. And so this maximum possible value occurs when you have the MLE plugged into the likelihood function, and I get 0.001194. So let's go ahead and take the ratio, 0.8179, so that we can see we're kind of getting closer to 1. Remember what that means. When I take negative 2 log lambda, I get 0.4020. Now, again, that's kind of close to 0. Relative to a chi-square distribution that's 1 degree of freedom, is that unusual to have a value of 0.4020? Well, the answer is no. Look at what my critical value would be. Let's say the 0.95 quantile from a chi-square distribution. So if I were to draw it out, I would have roughly something that looks like this. Here's 3.84. Here's my test statistic value. And we can see it's in a likely area for a chi-square an observed value for a chi-squared random variable. So therefore, I would say reject HO. If instead I had negative 2 log lambda out there, well, it's very unlikely to be that far out on the distribution because I have very little probability there. So in that case, I would say reject HO. How would I calculate a p-value? Well, I could take the probability that A is greater than 0.4020, where A has a chi-squared distribution with 1 degree of freedom. I could calculate my p-value like this. Okay, so there is not sufficient evidence to reject the null hypothesis. That then concludes this very short set of notes on doing a hypothesis test for pi.